Late in 1943, as the air war over Europe ground on without pause, a single American fighter dropped out of the winter sky and came down behind German lines. It was not a clean landing. The aircraft limped in low, scarred, uneven, its engine coughing through the final seconds of flight. By every expectation of Luftwaffe recovery crews, it should have been a wreck, twisted metal scattered across a field. Instead, it slid to a stop, largely intact, stubbornly whole, as if refusing to collapse even after the battle was over. The men who approached it did so cautiously. This was not curiosity at first, but habit. Enemy machines were often booby-trapped, their remains unpredictable. Yet, as they circled the aircraft, another realization took hold. The wings were punched through by heavy-caliber fire. The fuselage carried long, ugly scars where shells had torn through aluminum. The tail showed damage that, on most fighters, would have meant immediate loss of control. And still, the structure had held. Control surfaces were bent, not broken. Cables were strained but connected. The aircraft had remained flyable long enough to cross hostile airspace and reach the ground under its own power. Even more unsettling was the cockpit. Inside, the pilot had survived. He had endured impacts and damage that doctrine said were fatal. This was not luck measured in inches. This was something designed. German personnel were trained to recognize coincidence. They were equally trained to dismiss it. But as engineers were called in and the damage cataloged, coincidence became harder to defend. The pattern was too consistent. This machine had not merely survived a hit, it had absorbed punishment repeatedly, distributing it, tolerating it, refusing to fail where failure was expected. There was no secret weapon visible, no radical shape, no revolutionary material. What lay before them was something far more disturbing. An aircraft that seemed to accept damage as a condition of combat, not an exception. A fighter built not to avoid being hit, but to endure it. Quietly, the decision was made. This was not scrap to be cleared away. It was evidence. The aircraft was transported inland, away from the front, to be opened carefully and examined piece by piece. Somewhere inside its battered frame, German engineers believed, was an explanation. And once they began to look inside, the questions would only deepen. The examination began without ceremony. German engineers approached the Thunderbolt the way they approached all captured machines, slowly, systematically, with notebooks already open. Panels were removed in sequence. Measurements were taken. Weight was recorded. They expected cleverness, a hidden aerodynamic trick, a novel alloy, some elegant solution concealed beneath rough skin. That was, after all, how superiority was supposed to reveal itself. What they found instead was thickness. Beneath the outer panels, the structure felt heavy in the hands. Longerons were broader than expected. Frames were spaced generously, almost wastefully. Where European fighters pursued tight tolerances and minimal margins, this aircraft carried material as if it had room to spare. Armor plates surrounded the cockpit in places doctrine explicitly warned against. Weight here reduced climb. Weight here dulled agility. And yet the plate was there, deliberate, unapologetic. As the aircraft opened further, the pattern repeated. Systems were not refined to a single perfect solution. They were duplicated. Hydraulic lines ran alongside backups. Control linkages could fail without immediate catastrophe. Wiring looms were thicker, less delicate, easier to trace and replace. This was not optimization in the German sense. It was insurance. The engine told the same story. The massive radial dominated the forward fuselage, surrounded by structure designed not merely to mount it, but to protect it. Components were oversized, tolerances forgiving. Nothing about the layout suggested fragility. Nothing assumed ideal conditions. The machine seemed to anticipate dirt, vibration, damage conditions engineers were trained to minimize, not accommodate. There was an unsettling absence of cleverness. No single innovation explained the aircraft's survival. Instead, survival emerged from accumulation. More metal, more space, more margin. Each choice, viewed alone, looked inefficient. Taken together, They formed a system that resisted failure through sheer stubbornness. One engineer reportedly remarked that the aircraft felt less like a fighter and more like a flying machine shop. The comparison lingered because it fit. This was a machine, designed to be worked on, repaired, kept alive. It did not demand perfection from those who built it or those who flew it. As the last panels were removed and the notes compared, an uncomfortable thought began to surface. If this aircraft reflected its nation's thinking, then what they were seeing was not excess, it was intent. And intent, once recognized, is far harder to dismiss. For decades, European fighter design had followed a disciplined logic. Precision was virtue. Efficiency was survival. Every kilogram carried into the sky was weighed against climb rate, turn radius, and speed. Weight was not merely undesirable, it was the enemy. Engineers were trained to remove it wherever possible, to pare machines down to their most refined form. In combat, performance was protection. The American fighter on the hangar floor defied that belief at every turn. The Thunderbolt did not apologize for its mass. It carried it openly, built around it. Where German doctrine demanded elegance, this aircraft accepted bluntness. Its lines were not sculpted for minimum drag alone, but shaped to house fuel, armor, and structure. It did not seek to be untouched. It sought to remain alive after contact. Drag, too, had been treated as a failing something to be eliminated through careful aerodynamic compromise. Yet the P-47 tolerated it. External loads, thick wings, and a large frontal profile all suggested inefficiency. But endurance was the trade. Range was the prize. This fighter was not designed for short, perfect engagements. It was designed to go far, stay long, and return damaged. Finesse, the traditional measure of a pilot's art, mattered less here. The aircraft did not demand flawless handling to survive. It offered margin instead, room for error, room for damage, room for exhaustion. Control authority remained even when the airframe was wounded. Stability replaced delicacy. Predictability replaced sharpness. To German engineers, this was deeply unsettling. It violated assumptions not only about aerodynamics, but about the relationship between man and machine. European fighters were built to reward skill. This one seemed built to protect it. The machine absorbed risk so the pilot did not have to carry it alone. Gradually, the realization took shape. This was not ignorance of European principles, it was a conscious rejection of them. Somewhere in the design process, a different question had been asked, not how to build the best fighter in ideal conditions, but how to keep a pilot alive when conditions collapsed. As the engineers compared notes, another thought emerged, quieter but more profound. If this philosophy extended beyond a single aircraft, if it reflected a broader industrial mindset, then what they were studying was not merely a fighter. It was a warning about how the war itself was being engineered. German aviation culture entered the war with confidence earned through discipline. Its engineers were heirs to a tradition that prized refinement, balance, and control. Fighters were conceived as precise instruments, tuned carefully to operate within narrow performance envelopes. Speed, climb, and maneuver were not independent qualities, but parts of a carefully managed equation. Excellence came from harmony. Nothing unnecessary was permitted to remain. Within this framework, engineering assumed an ideal partnership between man and machine. Pilots were trained to exceptional standards, expected to master aircraft that demanded attention and rewarded precision. The fighter was not meant to forgive error, it was meant to amplify skill. Survival lay in anticipation, timing, and control. A perfect machine flown by a capable pilot was considered the highest expression of air combat. Maintenance reflected the same philosophy. Aircraft were not designed for casual handling. Repairs were specialist work, conducted by trained ground crews under controlled conditions. Accessibility mattered less than compactness. Complexity was accepted only when it served performance. Each additional system was a liability unless it delivered measurable advantage. Efficiency was not merely economical, it was moral. Waste implied weakness. Within this worldview, superiority was visible and immediate. A better aircraft climbed faster, turned tighter, struck first. Victory appeared as a series of decisive moments, won through brilliance and technical mastery. Attrition was something to be avoided, not embraced. The ideal war in the air was short, sharp, and resolved by quality. This was the mental framework German engineers carried with them as they approached the captured Thunderbolt. They expected to uncover a clever solution that explained its success, a refined aerodynamic compromise, an innovative material, a precise optimization hidden beneath a rugged exterior. Perhaps American industry, they believed, had stumbled upon a shortcut, something that delivered performance without the discipline required to sustain it. Instead, they found a machine that fit none of their assumptions. The Thunderbolt did not appear balanced in the traditional sense. Its performance envelope was broad rather than sharp. It did not demand perfection from its pilot, nor did it punish deviation as harshly as German fighters did. Maintenance access suggested anticipation of frequent repair rather than rare intervention. Systems existed not because they were elegant, but because they reduced the consequences of failure. To engineers trained to equate efficiency with superiority, this was disorienting. The aircraft seemed to violate the unwritten rules of good design. It carried redundancy where there should have been refinement. It accepted mass where lightness had always been king. It tolerated imperfection instead of eliminating it. At first, this was interpreted as inferiority, evidence of industrial carelessness, or doctrinal immaturity. But as reports accumulated and comparisons deepened, doubt crept in. If the Thunderbolt was truly flawed, why did its pilots keep returning? Why did damaged aircraft continue to appear in the sky? The most unsettling possibility had not yet been voiced, that the expectations themselves might be wrong. And if they were, then the engineers were not just studying an enemy aircraft. They were confronting the limits of their own belief system. What emerged from the disassembly was not refinement, but preparation for abuse. The Thunderbolt was not designed around ideal flight profiles or flawless execution. It was designed around what actually happened in combat: misjudged dives, flak bursts, clipped wings, ruptured lines. Where German engineers worked to prevent failure, this aircraft worked to survive it. The internal layout made that philosophy unmistakable. Components were not packed tightly together in pursuit of compactness. They were spaced deliberately, leaving room for access, removal, and replacement. A mechanic could reach vital systems without dismantling half the aircraft. In engineering terms, this was inefficient. In operational terms, it meant speed back into the air, speed back into the fight. Nowhere was the intent clearer than in the cockpit. Armor plates surrounded the pilot with an almost aggressive emphasis. Steel sat behind the seat, around the head, beneath the instrument panel. It added weight where every handbook warned against it. Yet the logic was blunt and unapologetic. If the pilot lived, the aircraft still mattered. If he did not, performance figures were irrelevant. Systems throughout the aircraft reflected the same calculation. Failure was not treated as a catastrophe, but as a condition to be managed. Hydraulic systems could be damaged without total loss of control. Electrical failures did not immediately silence the aircraft. Control surfaces retained authority even when partially compromised. The Thunderbolt did not collapse when wounded. It degraded gradually, buying time. Manufacturing choices reinforced this attitude. Tolerances favored speed of production over aesthetic precision. Parts were built to be good enough consistently, rather than perfect occasionally. This was not a lack of skill, it was a prioritization of scale. The aircraft assumed it would be built in large numbers, flown hard, damaged often, and repaired repeatedly. It was not precious. Repairs, in fact, were not an afterthought. They were expected. Field modifications, patched panels, mismatched parts, none of this violated the aircraft's logic. The structure tolerated them. The machine accepted human hands and imperfect fixes without protest. In doing so, it reduced downtime and returned pilots to combat faster than doctrine would have allowed. To German engineers, this accumulation of choices produced a troubling conclusion. Survival here was not accidental. It was engineered deliberately, layer by layer, decision by decision. The Thunderbolt did not rely on avoiding danger. It relied on enduring it. This inverted a deeply held belief. In European design culture, survival was the byproduct of superiority. In this aircraft, superiority emerged from survival. Each pilot who returned flew again. Each aircraft that absorbed damage carried experience forward instead of losing it in flame. As the reports were finalized, arrogance gave way to unease. The engineers had not uncovered crude improvisation. They had uncovered coherence, a system that assumed loss, planned for damage, and refused to be surprised by either. And once that logic was seen clearly, it became impossible to ignore the question it raised. If this aircraft was built to endure war as it truly was, what did that say about the war still to come? By late 1943, the captured Thunderbolt no longer appeared as an isolated curiosity. To the engineers studying it, the aircraft had become a reference point, evidence of a deeper divide between two nations approaching the same war from fundamentally different directions. This was no longer a question of technical preference, it was a collision of philosophies. Germany built fighters as precision instruments. Each aircraft was conceived as a finely balanced system, tuned to extract maximum performance from limited resources. Scarcity shaped every decision. Materials were conserved, engines pushed hard, airframes kept lean. The fighter was expected to win quickly, decisively, before its limitations became liabilities. Conservation was not optional, it was survival. American design assumed the opposite. The Thunderbolt reflected an industrial culture that planned for abundance and replacement. It accepted that machines would be lost, damaged, worn down. Instead of resisting that reality, it incorporated it. Aircraft were built to be produced in vast numbers, repaired repeatedly, and returned to service with minimal delay. Where German engineers saw waste, Americans saw margin. This difference extended beyond materials into assumptions about time. German fighters were optimized for moments, interceptions, brief engagements, sharp climbs to meet bombers at altitude. The aircraft was strongest at the peak of its performance curve. The American fighter was built for duration. Range, endurance, and persistence mattered more than perfection in any single phase of flight. It was designed to stay present. Protection revealed the contrast most clearly. German design protected performance first. If an aircraft retained its speed and agility, the pilot could avoid danger. Armor was added sparingly, only when it did not compromise the machine's essence. Survival depended on not being hit. American design inverted that logic. The Thunderbolt assumed the pilot would be hit. Protection came first, even if performance paid the price. This shaped behavior in the air. German pilots were trained to preserve their machines, to disengage when conditions turned unfavorable. American pilots flew with the knowledge that damage did not automatically mean death. Risk was managed differently. Engagement stretched longer. Missions were repeated. Experience accumulated. What the engineers gradually understood was that these philosophies were not abstract. They were already colliding thousands of meters above Europe. Each engagement tested not just aircraft, but systems, training pipelines, maintenance capacity, industrial output. One side fought to preserve excellence, the other fought to sustain presence. At first, the results were ambiguous. Precision could still prevail in individual encounters. Superior handling could still win duels. But the engineers sensed something shifting beneath those moments. A war fought by instruments required constant perfection. A war fought by tools tolerated wear. As reports from the front accumulated, the question sharpened. If air combat was becoming less about brilliance and more about endurance, then which philosophy would outlast the other? The answer was not yet visible in the sky, but it was already taking shape on the ground, in factories, airfields, and repair depots, places where wars are decided long before they are concluded. In the air, the Thunderbolt appeared to confirm every European prejudice about American design. It was large, it was heavy. In a turning fight, it bled energy quickly, unable to match the tight, elegant circles of lighter German fighters. In the vertical, it climbed more slowly, its mass exacting a visible price. To pilots trained to judge an opponent by these measures, the conclusion seemed obvious. This was not a dangerous aircraft. It was merely a durable one. Early encounters reinforced that belief. German pilots, many of them veterans of years of combat, saw the P-47 as something to be managed rather than feared. It could be outturned. It could be outclimbed. In the familiar geometry of European air combat, it looked wrong, too blunt, too slow to respond, too reliant on momentum. Against finesse, it appeared unsophisticated. But air combat rarely unfolds according to first impressions. What German pilots began to notice, often too late, was what happened when the fight broke downward. The Thunderbolt did not float, it fell. Its mass, once a liability, became an advantage. In a dive, it accelerated relentlessly, compressibility effects setting in before lighter aircraft could follow safely. Where other fighters hesitated, the P-47 continued, trading altitude for speed with unnerving confidence. More unsettling was what happened after contact. Cannon hits that should have crippled an aircraft failed to produce immediate results. Control surfaces remained responsive. Engines continued to run. Smoke trailed, but the fighter did not disintegrate. Pilots watched Thunderbolts absorb damage, roll away, and dive out of reach alive when doctrine said they should be dead. At first, these moments were dismissed as exceptions. Luck, poor hits, faulty ammunition. But exceptions, when repeated, become patterns, and patterns demand explanation. German pilots began encountering the same aircraft more than once. Familiar markings reappeared in the sky days later, sometimes weeks later. The same pilots returned, their machines patched, scarred, unmistakably used. Combat reports noted this persistence without fully understanding it. Attrition, long assumed to favor precision, was behaving differently. For American pilots, the experience was equally formative. They flew, knowing that the aircraft beneath them was built to endure mistakes and damage. This knowledge did not make them reckless, but it altered their calculus. Engagements were pressed longer. Attacks were repeated. Disengagement was possible without surrendering the aircraft to gravity or flame. Survival was not guaranteed, but it was plausible. This feedback loop survival enabling experience enabling survival quietly reshaped combat effectiveness. The Thunderbolt's limitations remained. It would never be a dogfighter in the traditional sense. But it did not need to be. It needed to keep its pilots alive long enough to learn, adapt, and return. Gradually, the tone of German assessments changed. The aircraft was no longer merely clumsy. It was resilient. Not graceful, but persistent. Not superior in isolation, but difficult to eliminate. The Thunderbolt's reputation shifted from mockery to caution, and then to respect. What had once looked wrong now looked intentional. Engineers and pilots alike began to grasp that the P-47 was not designed to win elegant duels. It was designed to survive a brutal environment long enough to impose pressure over time. Each sortie added weight not to a single engagement, but to a campaign. The aircraft's true performance was measured not in seconds of maneuver, but in weeks of sustained presence. By the time this understanding settled in, it was already influencing behavior on both sides. German pilots chose targets more carefully. American formations pressed deeper, staying longer. The sky itself seemed to favor endurance over brilliance. And as reputation hardened into reality, a deeper question emerged, one that would shape everything that followed. If an aircraft that looked wrong could survive, adapt, and return again and again, then perhaps the rules of air combat were changing. The answer would not come from a single battle, but from what happened when damaged aircraft came home and what that survival made possible next. Survivability is not a dramatic quality. It does not announce itself in a single maneuver or a moment of brilliance. It works quietly, accumulating its effects over time. In the Thunderbolt, American pilots flew with the understanding that damage did not automatically mean death. This knowledge did not remove fear, but it changed its shape. Fear no longer ended every decision. It could be managed. That shift altered behavior in subtle but decisive ways. Pilots pressed attacks a little longer, stayed on target a few seconds more, knowing that a hit did not always end the mission. Aggression increased, not recklessly, but deliberately. The aircraft beneath them absorbed risk that would otherwise have rested entirely on the pilot's judgment. Combat became less brittle. As missions accumulated, another effect emerged. Crews survived to fly again. Sorties were no longer isolated events, but chapters in a continuous experience. Pilots learned enemy habits, recognized patterns in interception, understood where flak was heaviest and where it thinned. Experience did not vanish in a plume of smoke, it stayed, returning to the airfield, climbing back into the cockpit the next morning. This continuity mattered more than any single engagement. Air combat rewards familiarity. With one's aircraft, with formation partners, with the rhythm of combat itself. The Thunderbolt's survivability preserved this familiarity. It protected not just lives, but learning. Each damaged aircraft that returned carried more than scars. It carried knowledge. German pilots began to notice. Familiar opponents reappeared in the sky, their aircraft patched, their tactics sharper. Encounters were no longer with unknown quantities, but with men who had survived before and adapted. The psychological balance shifted. The assumption that damage equaled elimination no longer held. Air combat lost some of its finality. On the German side, the contrast was stark. Precision fighters demanded careful handling and narrow margins. Damage often meant total loss. Pilots who fell did not return with lessons learned. They were replaced by those who had yet to acquire them. Experience leaked away steadily, even when individual engagements were won. Brilliance could triumph in moments, but it struggled to compound. Attrition, once assumed to favor the technically superior, began favoring endurance instead. The side that retained pilots retained effectiveness. The side that lost them repeatedly found itself relearning the same lessons under fire. This was not visible on any single combat report. It emerged slowly across months of operations. The Thunderbolt did not dominate the sky overnight. Its impact was cumulative. Each mission flown by a returning pilot increased the probability of success on the next. Each landing by a damaged aircraft preserved not only manpower but momentum. Survivability multiplied combat power by extending it through time. This was the quiet transformation German engineers had begun to fear. Air combat was becoming a long game. Victory no longer hinged on superior performance at the peak of capability, but on sustained presence across hundreds of engagements. The aircraft that could endure mistakes, absorb damage, and keep flying altered the balance without ever needing to be perfect. The shift was strategic as much as tactical. Endurance allowed pressure to be applied continuously. Escorts stayed with bombers longer. Fighters returned day after day. Resistance wore thin not through decisive blows, but through relentless repetition. By the time this dynamic was fully understood, it was already entrenched. Survivability had stopped being a defensive feature. It had become an offensive asset, a multiplier that transformed individual aircraft into a system capable of outlasting its opponent. And as air combat stretched into weeks and months instead of minutes, the decisive question changed. It was no longer who flew the better machine in ideal conditions. It was who could remain in the sky when conditions stopped being ideal. When the focus shifted from combat performance to maintenance, the Thunderbolt revealed its most consequential secret. German engineers turned their attention away from aerodynamics and armament and toward the evidence left behind by use. They examined field repairs, not factory drawings. What they found challenged assumptions more deeply than any performance figure. The repairs were often crude. Panels were patched rather than replaced. Rivet lines were uneven. Components bore marks of hurried removal and reinstallation. To an engineer trained in precision craftsmanship, the workmanship looked careless, even sloppy. And yet, the aircraft flew. Systems functioned. Structural integrity remained intact. The fixes held under stress. This was not accidental resilience. Access panels were positioned to allow rapid entry to critical systems. Components could be removed without disturbing adjacent structures. Repairs that would have grounded a German fighter for days or ended its service entirely could be completed in hours. The aircraft did not resist being worked on. It invited it. Damage tolerance played a central role. The Thunderbolt was designed to accept imperfections without cascading failure. A bent panel did not compromise flight. A damaged subsystem did not immediately disable the whole. This tolerance shortened turnaround time dramatically. Aircraft returned to service quickly, often still bearing visible scars. Function mattered more than appearance. For German engineers, this reframed the meaning of efficiency. In their tradition, efficiency was measured in optimal performance and minimal waste. Here, efficiency was measured in time. Time to repair, time to return, time to fly again. The Thunderbolt sacrificed elegance to gain continuity. It was designed not to avoid damage, but to recover from it. This reflected an industrial logic that extended far beyond the aircraft itself. American production assumed constant use and constant repair. Manufacturing lines fed maintenance depots as much as frontline squadrons. Spare parts were plentiful. Standardization simplified replacement. The system expected wear and planned for it. German aviation culture, by contrast, still treated aircraft as refined instruments. Repairs were acts of restoration, not routine. Craftsmanship mattered because machines were scarce. Each loss was deeply felt. Each damaged aircraft represented a drain on limited resources. The system strained under sustained use. The Thunderbolt inverted that equation. It treated aircraft as assets to be consumed gradually, not preserved delicately. Losses were absorbed. Damage was anticipated. Maintenance became a force multiplier rather than a bottleneck. The aircraft's value lay not in its perfection, but in its availability. This realization unsettled the engineers studying it. They had been searching for superiority in form and function. Instead, they found it in process. The Thunderbolt was not remarkable because it flew better on a perfect day. It was remarkable because it kept flying on imperfect ones. Gradually, a broader truth came into focus. Air power was no longer defined solely by speed, climb, or firepower. It was defined by logistics, the ability to sustain operations over time. The aircraft that could be repaired fastest, returned quickest, and flown most often accumulated advantage without ever appearing exceptional. In that sense, the Thunderbolt was not just a fighter. It was a node in a vast industrial network that valued continuity over brilliance. Each repaired aircraft represented not merely survival, but persistence. As German engineers closed their reports, the implication was clear and troubling. They were no longer studying how America fought in the air, they were studying how America fought wars. And once that distinction was understood, the implications reached far beyond a single captured aircraft. At first, the reports changed quietly. There was no announcement, no formal reversal of doctrine. Language shifted almost imperceptibly. Line by line. Early descriptions of the Thunderbolt had leaned heavily on inefficiency, excess weight, compromised agility, unnecessary redundancy. Now, different words began to appear. Resilient, persistent, difficult to destroy. This was not praise. It was acknowledgement. German engineers, trained to speak precisely, rarely altered terminology without reason. When they did, it reflected a change not only in assessment, but in understanding. The P-47 was no longer being measured against European ideals of refinement. It was being evaluated on its own terms, and on those terms it was performing exactly as designed. The realization emerged from synthesis rather than discovery. No single component explained the aircraft's effectiveness. It was the interaction of choices, armor, spacing, redundancy, repairability that produced the result. Perfection, the engineers noted, was not the objective. Continuity was. The Thunderbolt was built to keep functioning when perfection was impossible. This forced a reconsideration of first principles. In German doctrine, survival was achieved through superiority. The better machine, flown by the better pilot, avoided damage and ended the engagement quickly. In the American model revealed by the P-47, survival was engineered directly. The aircraft assumed that damage would occur. It planned for it, and in doing so, it preserved the pilot. That preservation carried consequences far beyond the cockpit. Each pilot who survived flew again. Each return added experience that could not be manufactured, accelerated, or replaced. Survival produced experience. And experience, compounded across hundreds of sorties, produced dominance. This was the most unsettling conclusion of all. Air superiority, the engineers realized, was no longer the product of isolated moments of brilliance. It was the outcome of accumulation. The side that retained pilots retained tactical memory. The side that lost them repeatedly fought with fresh hands and fading knowledge. Over time, even superior machines struggled to compensate. The reports began to reflect this understanding. The Thunderbolt was described not as a superior fighter but as a stabilizing force within the American system. It reduced loss rates, it extended pilot lifespans, it allowed training to mature into expertise. In doing so, it altered the statistical balance of the air war without ever needing to dominate individual engagements. For German engineers, this insight was deeply uncomfortable because it exposed a structural weakness. Germany could still produce excellent aircraft. It could still field highly skilled pilots. But it could not easily reproduce the conditions that made the Thunderbolt effective. Industrial scale was limited. Materials were constrained. Pilot training pipelines were under strain. Losses could not be absorbed indefinitely. Most troubling of all was the recognition that this imbalance was not temporary. It was systemic. The American approach did not rely on surprise or secrecy. It relied on endurance. And endurance, once established, was difficult to counter with innovation alone. The engineers understood now why copying the aircraft itself would not solve the problem. The Thunderbolt was an expression of a broader capacity, industrial, logistical, organizational. Without that foundation, replication was illusion. Insight did not equal capability. In private correspondence and internal memoranda, the tone grew somber. There was no panic, but there was clarity. The air war was no longer a contest that could be won solely through better design or superior tactics. It was becoming a test of systems, of which aircraft were only one component. This was the moment the engineers truly understood what they were facing. Not a single enemy machine, but an ecosystem designed to sustain pressure indefinitely. The Thunderbolt was simply the most visible manifestation of that logic. And once seen, it could not be unseen. As the reports were filed and the aircraft returned to storage, the engineers carried with them a realization that extended beyond aeronautics. They had uncovered not a flaw to exploit, but a principle to contend with. A way of war that favored survival over perfection, continuity over brilliance. The question that remained unspoken, but heavy, was whether a system built on scarcity could adapt fast enough to confront one built on endurance. The answer would soon be written, not in reports, but in the skies above Europe. Understanding a problem does not guarantee the ability to solve it. German engineers, having grasped the logic behind the Thunderbolt's resilience, now faced a more sobering reality. The philosophy they had uncovered could not be adopted by decree. It was rooted not in a single design choice, but in an entire industrial ecosystem one Germany did not possess. American aircraft were born from scale, factories stretched across a continent, supplied by secure shipping lanes and abundant raw materials. Aluminum, fuel, rubber, and steel flowed in quantities that allowed inefficiency to be tolerated. Losses could be replaced, damage could be absorbed, production schedules assumed interruption and overcame it through volume. Germany operated under none of these conditions. By late 1943, materials were already scarce. Strategic bombing disrupted supply chains, specialized alloys were rationed, fuel shortages dictated training hours and operational tempo. Every additional kilogram added to an aircraft required justification because it carried opportunity cost elsewhere. A design philosophy that embraced redundancy and excess was structurally incompatible with this reality. Production itself was fragmented. German aircraft manufacturing was spread across dispersed facilities, often reliant on skilled craftsmanship rather than standardized processes. This allowed for refinement, but limited speed and interchangeability. Components were not always uniform. Repairs demanded expertise. Scaling such a system to match American output was not merely difficult, it was impossible under wartime pressure. Pilot replacement posed an even deeper constraint. German training pipelines had been designed for quality, not quantity. Early war success had reinforced this approach. But as attrition increased, experience drained away faster than it could be replenished. The Thunderbolt's philosophy depended on preserving pilots long enough for experience to compound. Germany lacked the margins to do the same. Even when individual engineers proposed changes, additional armor, simplified systems, improved repairability implementation, stalled. Each modification rippled through an already strained system. Added weight reduced performance. Increased production time delayed delivery. The system resisted change because it had been optimized for a different kind of war. More importantly, the Thunderbolt's resilience was not the result of improvisation. It reflected decisions made years earlier, before combat demanded them. Factories had been designed around standardization. Logistics networks had been built to support constant repair. Training assumed sustained operations. These were peacetime investments paying wartime dividends. Germany had no equivalent reserve. Adaptation required time, resources, and freedom from immediate crisis, none of which were available. The insight arrived too late. The war had already locked systems into place. This was the harshest lesson for the engineers involved. They had not failed to recognize the problem, they had failed to build the conditions that made the solution possible. The Thunderbolt could not be copied because it was not merely an aircraft. It was the visible edge of a deeper structure, industrial, organizational, and strategic. Insight, they realized, does not equal capability. An aircraft can be studied. A philosophy can be understood, but a system built over decades cannot be replicated in months. Germany's war effort had been shaped by constraint and urgency. America's had been shaped by anticipation and scale. When those approaches finally met in the air, the outcome was already constrained by choices made long before the first shots were fired. The engineers recorded their conclusions carefully, aware of their implications. There was no single countermeasure to recommend. No technical fix to propose. The imbalance they observed was not tactical, it was structural. As the reports circulated, they carried a quiet finality. The Thunderbolt had revealed not only why America's air power endured, but why Germany's could not adapt fast enough to stop it. And with that understanding came a deeper realization. The decisive battles of the air war were no longer ahead. They had already been fought in factories, in training programs, and in the assumptions that governed how nations prepared for war. The consequences of rugged design did not announce themselves in headlines or communiques. They unfolded quietly, sortie by sortie, in patterns that only became visible over time. American pilots survived their missions and returned. Then they flew again, and again. Each return was small, almost unremarkable on its own. Together, they altered the structure of the air war. Escort missions began to stretch farther into enemy territory. What had once been brief protective windows around bomber formations expanded into sustained presence. Fighters stayed with the bombers longer, remaining overhead deep into hostile airspace where losses had previously been accepted as inevitable. The Thunderbolt's endurance and survivability made this possible, not through dominance, but through persistence. Bomber losses did not collapse overnight. They decreased incrementally. A few fewer aircraft lost on one mission, a few more crews returning the next day. These marginal gains compounded. Each reduction preserved trained airmen, preserved experience, preserved morale. The bombing campaign did not suddenly become safe. It became survivable. As weeks passed into months, air superiority began to take shape not as a single victory, but as a condition. American formations arrived consistently, escorted by pilots who knew the routes, the defenses, the enemy's habits. German interceptors faced opponents who had already survived multiple engagements, who had learned when to press and when to disengage. Familiarity replaced improvisation. The imbalance was subtle but decisive. German pilots still fought with skill and courage. Their aircraft still possessed impressive performance. But they increasingly faced adversaries who were not learning for the first time. Experience met experience unevenly. One side accumulated it, the other bled it away. This dynamic reshaped the tactical environment. Interceptions became riskier. Attacks had to be pressed harder to achieve the same effect. Losses mounted among those who could least afford them. Replacement pilots entered combat with fewer hours, less preparation, and against enemies who had already adapted. No single battle marked the turning point. There was no decisive clash in which the skies changed hands. Instead, the balance shifted through repetition. Each successful escort mission reinforced the next. Each surviving pilot extended the reach of American air power by a little more. Gradually, resistance thinned. From the ground, the change was unmistakable. Bombers arrived more regularly. Targets once struck intermittently were now hit systematically. Repair efforts lagged behind damage. Industrial nodes came under sustained pressure. The air war ceased to be episodic. It became continuous. For German planners, this was the most dangerous development of all. Their defenses had been designed to blunt raids, not absorb constant presence. Interceptors could still inflict losses, but not at a rate that altered the trajectory. The initiative slipped away not through defeat, but through exhaustion. The Thunderbolt's role in this transformation was indirect but essential. It did not win the air war alone. It enabled a system that could endure long enough to impose pressure without pause. Its ruggedness preserved pilots. Preserved momentum. Momentum reshaped strategy. Air superiority, once achieved, reinforced itself. Experienced escorts reduced bomber losses. Reduced losses sustained operational tempo. Sustained tempo overwhelmed defenses. Each layer supported the next. The structure held because it was built to absorb stress rather than collapse under it. By the time this was fully apparent, the war in the air had already tilted. German interceptors still rose to meet formations, but they did so under increasingly unfavorable conditions. Their opponents were no longer testing a theory. They were executing a mature system. The Thunderbolt's rugged design had done more than keep pilots alive. It had bought time for experience to accumulate, for pressure to build, for superiority to emerge without spectacle. The decisive shift occurred not in moments of brilliance, but in the steady erosion of resistance. As the skies over Europe filled day after day with escorted bombers, one truth became unavoidable. The outcome was no longer in doubt. It was being written gradually, relentlessly, by machines designed not to be perfect, but to endure. And with each mission that returned intact, the war in the air moved further from contention and closer to conclusion. By the time the Thunderbolt's impact was fully understood, it was clear that no single aircraft could explain what was happening in the skies over Europe. The P-47 was not a miracle weapon. It did not overturn the balance through sudden superiority or revolutionary performance. Instead, it revealed something larger and far more consequential. Air power had become industrial power. The Thunderbolt functioned as part of a system whose elements were tightly aligned. Design anticipated damage. Production anticipated loss. Maintenance anticipated repair. Training anticipated repetition. Each component reinforced the others, creating a structure that could absorb stress without collapsing. The aircraft itself was only the visible surface of that structure. Losses. Once the great limiter of air operations, no longer produced immediate strategic shock. Aircraft were replaced. Pilots survived to fly again. Units recovered from setbacks without losing cohesion. This resilience altered the tempo of war. Operations no longer paused to recover strength. Strength was regenerated continuously. German air power, by contrast, still rested heavily on brilliance. Exceptional aircraft designs, skilled pilots, and tactical ingenuity produced moments of remarkable effectiveness. But brilliance, by its nature, does not scale easily. It depends on individuals, on conditions, on narrow margins. When pressure increased, those margins vanished. As American operations intensified, the difference became stark. One system expanded under strain, the other tightened. German units were forced to commit experienced pilots repeatedly, accelerating loss. Training shortened. Aircraft were pushed harder. Maintenance suffered. The system strained not because it lacked quality, but because it lacked depth. Air combat increasingly took on an attritional character. Engagements were no longer isolated contests of skill. They were iterations in a prolonged process. Each sortie mattered less for its immediate outcome than for what it preserved or consumed. Survival added weight to the future. Loss subtracted from it. The Thunderbolt embodied this shift. Its value was not measured by kill ratios alone, but by continuity. It enabled pressure to be applied steadily, without interruption. It allowed American air power to behave less like a weapon and more like a force constant, cumulative, and difficult to escape. Over time, predictability emerged, not in individual battles, which remained uncertain and dangerous, but in trajectory. The side that could replace losses faster than it incurred them gained leverage. The side that could retain experience longer than it lost, it gained momentum. These dynamics operated quietly, indifferent to heroism or ingenuity. German brilliance continued to extract a price. American losses never disappeared. But the exchange no longer threatened collapse. The system absorbed punishment and continued forward. What had once been contested airspace became increasingly controlled, not through sudden conquest, but through sustained presence. This was the moment when air power ceased to be defined by aircraft alone. It became an expression of national capacity of factories, logistics, training pipelines, and doctrine working in concert. The Thunderbolt did not create that capacity. It revealed it. For German planners and engineers, the implication was unmistakable. They were no longer fighting an enemy that needed to be outthought or outflown in isolated moments. They were facing an opponent whose strength grew through use, whose losses sharpened rather than weakened it. Air combat, once a test of finesse, had become a test of endurance. And endurance favored the system that could scale without breaking. By the time this transformation was fully visible, the outcome had already taken shape. Not because defeat was inevitable in any single encounter, but because the larger contest had moved beyond tactics. The war in the air was no longer being decided by who flew best. It was being decided by who could keep flying longest. By the time the captured Thunderbolt had yielded all it could, its lesson no longer belonged to engineers alone. It had become explanatory. The aircraft did not reveal why America built a better fighter in isolation. It explained why America built a different kind of air power altogether. American air power was never centered on superiority per aircraft. No single machine needed to outfly every opponent in every regime. What mattered was survivability across thousands of sorties, across days, months, and seasons of sustained combat. The Thunderbolt embodied that priority. It existed not to win perfect fights, but to remain present in imperfect ones. This distinction mattered because wars are not decided by averages. They are decided by accumulation. An aircraft that survives damage preserves a pilot. A pilot who survives accumulates experience. Experience, repeated across formations, becomes reliability. Reliability becomes pressure. Pressure becomes control. The P-47 fit into that chain precisely where it mattered most. Engineering, in this system, served strategy rather than ego. Decisions were not made to impress peers or satisfy theoretical ideals. They were made to solve operational problems at scale. Armor was added not because it was elegant, but because pilots were being lost. Redundancy was accepted not because it was clever, but because missions could not stop. The machine bent to the war, not the other way around. Industrial margin, once dismissed as waste, became tactical advantage. Extra metal absorbed extra damage. Extra fuel extended presence. Extra parts reduced downtime. These margins compounded quietly, turning abundance into leverage. The Thunderbolt did not need to be exceptional. It needed to be sufficient repeatedly. Perfection, long treated as the hallmark of excellence, revealed its fragility under sustained stress. Precision aircraft demanded ideal conditions to shine. When those conditions eroded through attrition, fatigue, scarcity, the system faltered. Ruggedness, by contrast, thrived in degradation. It assumed imperfection and endured it. This was the deeper meaning German engineers had uncovered without being able to replicate it. The captured aircraft explained why their assumptions, though logical, were incomplete. They had designed machines for brilliance. America had designed machines for continuity. In a prolonged war, continuity proved decisive. Modern air war began to take shape in that realization. Air superiority emerged not as a moment, but as a condition maintained through logistics, training, repair, and survivability. Aircraft were no longer judged solely by how they performed at their limits, but by how long they could remain useful once those limits were exceeded. The Thunderbolt did not signal this transformation alone, but it clarified it with unusual honesty. Its battered airframe told a story written in damage and repair, in pilots who returned, in missions flown again. It showed that the future of air power lay not in flawless execution, but in resilient systems. When the engineers closed the hangar doors, they understood that they had not discovered a secret weapon. They had uncovered a philosophy made metal, a belief that machines should forgive mistakes, a belief that pilots should live, a belief that wars are won by systems capable of enduring reality rather than denying it. The captured P-47 explained why the air war was no longer a contest of duels. It was becoming a contest of endurance, organization, and time. And once that truth was visible, the final shape of the conflict could already be seen, forming beyond the hangar walls carried aloft day after day by aircraft built not for perfection, but for persistence. When the examination finally ended, the aircraft was closed again. Panels were refitted, notes were filed. The Thunderbolt was returned to storage, its role as an object of study complete. For the German engineers involved, the moment carried a quiet finality. They understood now what the machine meant, and understanding in this case brought no comfort. They had not found a secret weapon. There was no breakthrough material, no revolutionary mechanism, no single insight that could be isolated and countered. What they had uncovered was more difficult to confront. A philosophy embedded in aluminum, steel, and rivets. A way of thinking about war that extended far beyond a single aircraft. At its core was a simple belief that pilots should live. Not as an abstract ideal, but as a practical requirement. Armor was added not to win arguments, but to save lives. Redundancy existed not to impress engineers, but to give men a chance to come home. The aircraft assumed that fear, fatigue, and error were unavoidable, and it refused to make them fatal. Closely tied to this was another belief that machines should endure mistakes. The Thunderbolt did not demand perfection from those who flew or repaired it. It absorbed misjudgment. It tolerated damage. It continued functioning when conditions degraded. In doing so, it aligned itself with reality rather than theory. The engineers understood that this was not accidental kindness. It was strategic clarity. A pilot who survives flies again. A machine that endures keeps pressure on the enemy. Survival preserves experience, and experience compounds. What appeared humane was also ruthlessly effective. The final belief was the most decisive of all, that wars are won by systems, not duels. German aviation culture had been built around mastery of aircraft, of technique, of moments. Excellence was concentrated in individuals and in machines refined to their limits. But the Thunderbolt revealed a different path. Victory could emerge not from brilliance, but from inevitability, from systems designed to function under stress, scale under demand, and continue despite loss. The engineers had searched for brilliance inside the P-47. They had expected to find ingenuity concentrated in a clever solution. Instead, they found inevitability distributed across a system too large to outmaneuver and too resilient to exhaust quickly. This realization lingered because it extended beyond aviation. It explained patterns already visible across the war, factories replacing losses faster than they occurred, training pipelines, feeding experience back into the front, logistics sustaining pressure without pause. The aircraft was only one expression of that momentum. Standing before the closed machine, the engineers knew they could describe what they had seen, but not undo it. The Thunderbolt could be countered tactically, damaged operationally, even destroyed individually. But the philosophy it represented could not be bombed away easily. It was rooted in preparation, scale, and acceptance of reality. The lesson hidden in the metal was therefore not technical. It was moral and strategic at once. It suggested that humility toward imperfection was stronger than confidence in perfection. That endurance outlasted brilliance. That systems built to survive reality would eventually overwhelm those built to transcend it. Long after the aircraft was gone from the hangar floor, that lesson remained. It echoed in the skies over Europe as formations returned day after day. It echoed in the gradual tilt of the air war. achieved without spectacle and without pause. They had searched the thunderbolt for genius. What they found instead was a future already set in motion, one in which wars were decided not by who flew best in a moment, but by who could endure longest over time. They laughed once. They did not laugh again.